Hi everyone, in this video we are going to discuss waves of light. So hopefully at this point we understand that light or electromagnetic radiation transposes itself through space, or it travels through space in wave-like patterns, okay? So it moves like a wave. And so we're going to talk about waves in this video, but specifically we're trying to nail down two definitions. We want to talk about wavelength and we want to talk about frequency. So let's draw out just a classic wave right now, so we can get a picture here. So we have an end and a start. Normally you start right here where it crosses, and so you just kind of go up and down and up and down and up, and I like to end there. That's fine. All right, so we're going to start off with wavelength. Wavelength is one of the easiest ones to define. It simply is exactly what it sounds like. How long is your wave? Now, how do we define a wave? Well, a wave is defined as a peak to peak. Okay, so you go all the way down here and then all the way up. That's one wave. I personally think it's easier to think of it if you start right here and you go one hump up and then one hump down and you're back to the beginning. So you do it again, one and one. So from here to here, that would be one wavelength. So a wavelength is simply a measure of the distance between peaks. Okay, usually we use the unit meter or nanometer. Nanometer is one I want you to get very comfortable with because that's our visible region. But the big thing we need to understand is that it's represented by this lambda. Okay, so it looks like that. So if I were to redraw out a wave, because that starts to look really sloppy. So let's say we just go from here to here, and we'll just do something with two wavelengths. So we go up and down, here's one wavelength, and then up and down, here's two wavelengths. So we could define it from here to here. That right there is one wavelength, okay? So you need to get very, very comfortable with that. Now the next thing we want to talk about is frequency. So frequency is simply a measure of rate, okay? So frequency is just the number of waves per second. So we're very specific about the unit of time here for frequency. So think about if you and someone else were walking down the street and how quickly you walk. So I personally walk really, really fast. So I would have a fast frequency. So I'm just like, and I walk. My husband, however, lollygags. He takes forever. And so he's just like, na, 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 slow. He would have a very, very slow frequency. So in terms of waves, what you have to think about is if you have a fixed point right here and your waves are moving past it, we are trying to figure out how many waves pass in 1 second. So our second is our piece of time. And so we're watching. So if something goes like this, it's really, really fast. It's going to have a high frequency. If something is like this, it's taking its time. It has a very low frequency. So now, frequency has a very specific unit. It is in inverse seconds, okay? Sometimes we write inverse seconds as s to the -1, or we call it hertz, Hz. So hertz, it's actually named after a guy named Hertz. He kind of came up with a bunch of this stuff, and so we named after it, named frequency, the unit of frequency after him. It's just kind of an honor. But essentially, it's just a rate of something per time. So this is per second. So what we need to do is figure out how to relate frequency and waves. And so there's one very, very common equation that we use to do this, and it's C is equal to lambda times nu. Now, I'm realizing now I didn't tell you, this is nu. Frequency is represented by this funky little V, or nu. I kind of think of it as like a chic little V. It kind of has this little edge that comes off the side. And so our equation to relate these is you have the speed of light, which is represented by C. This is a constant. It's never going to change. Your speed of light is C, which is equal to 3 times 10 to the 8th meters per second. It's really fast, okay? 3 times 10 to the 8 meters in 1 second. That's really, really fast. Then you have your lambda, which is your wavelength. Remember, in this equation, we must use meters, and that's dictated by your constant speed of light. And then in frequency, you use 1/seconds, which is equal to hertz. Okay, so now we have our main equation that helps us go back and forth from wavelength and frequency, and I want you to actually do this and solve a problem. So if I tell you that green light, where's my pen? If green light, on average, has a wavelength of 500 nanometers, what is its frequency? Okay, go. All right, did we get an answer? Hopefully we did. If not, let's work through it together. So the first thing we need to do is identify our variables. So we have something which is 500 nanometers. Nanometers is your big red flag to know that we're talking about wavelength. So wavelength is equal to 500 nanometers. However, when we're talking about nanometers or wavelength, we absolutely must get that in terms of meters. So we're going to convert from nanometers to meters. So we know that we have, for every 1 nanometer, we have 1 times 10 to the negative 9th meter. So they're really, really small. So this is equal to 5 times 10 to the negative 7 meters. Here's one thing, if this is kind of tricky and you don't really understand the dimensional analysis, one way you could do this is just understand that nanometers is always times 10 to the negative 9. And so you could have just said your wavelength is equal to 500 times 10 to the negative 9 meters. Some people find that easier, but no, this is your scientific notation. This is not. This one is 2 points, okay? It has 3 digits in front of the decimal, and remember for scientific notation it can only be 1. So it's just a difference of how you want to do it. But if we're not asking you for scientific notation, I definitely would recommend this method. All right, so now you've got your number in terms of meters, and what we need to do is try to figure out what the frequency is. So we know that c is equal to lambda times nu. We know that our speed of light is equal to 3 times 10 to the 8th. We know that our wavelength is equal to 500 times 10 to the negative 9, or you could do 5 times 10 to the negative 7. It's the same. So this is meters per second. This is in meters, and then you're left with frequency. And so all you have to do is use your calculator and solve for frequency or for nu, and you should get an answer of equal to 6 times 10 to the 14th inverse seconds, or hertz. Okay, get very comfortable with hertz. That is the correct answer. So now what I want you to do is take it one step further, because I want to make sure you fully understand the relationship between frequency and wavelength. So let's complete this sentence. If frequency increases, then the wavelength must what? Finish that sentence.